Hi guys, welcome to my channel. Okay. Uh, Sometimes we can use the always statements for designing combinational logic also. Let's today design a 7-segment display decoder, that takes advantage of the case statement in Verilog. In that process, we'll learn about the case statement also and how we can use it. So yeah, let's proceed with the development. So I've already created this module as segment, shorthand for 7-segment display. It will accept input of 4-bit data, so 320 data, and will produce output. The output should be reg, again for the same reason, because this variable will assign inside an always state, and the output shall be of 7-bit, similar to the 7-segment bits. Segments. Okay, this is fine. Let's write the always statement now. Always @ star. So for combinational circuit, you will always use this syntax. You will always use always @ star if you are designing a combinational circuit using an always statement. Now, one advantage of the always statement is that you can write case statement now, which is similar to the switch case. So the format is like this: case and input shall be data. If my data is, let's say, the 7-segment decoding output is in the format of A, B, C, D, F, G. Okay. Usually Verilog ignores this underscore, so it is better for debugging purposes and helps the other designer understand your code as well. So for case 0, my output should be segments equal to what it should be: 7-bit, base is binary, and A, B, C should be 111, D, E, F should be also 111 and 0. Okay, now we have designed the logic for 0. One interesting thing to note that is that case will automatically consider it as decimal by default. Otherwise, you can like specify it like this also. So I specified it in decimals just so that it becomes easy. However, you may specify it like this also: 4-bit 000. This is also fine. And if you're like writing in decimal, that is also fine. Okay, now we'll generate other cases for one. So for one, A should be 0, B and C should be 1 1, others should be 0. So 3 0 here. Similarly, others for 2 it will be copy this as it is. For 2 what would be 1 0 1 1 0 1. For 3 triple 1 1 0 0. Okay, for 4 it will be 0 1 1 0 0 1 1. For 5 0 and rest also like you will be able to design it 5, 6, 7, 8, 9. Okay, I have just designed it before, so just pasting it. Okay, I'll write it 5 segment 101 1011 6 7 8 9. Again, you will have to like try to draw it manually and then assign this value. I have already like drawn it manually and directly writing values here now. Again, for 6 it will be 101. All ones. For 7 111 all 0. For 8 111 all 1. Okay, and for 9 it is proper. Now we'll write the default statement here using default. And by default the segment should have 0 value. All should be, output should be 0. Okay, so it will be all segments null value. However, this case may not arise only actually, but if your input goes above 10, okay, the case will not be detected and it will the control will flow to the default statement and output will be all the 7 bits to 0. This is done. Your case is now completed. Whenever writing your case statement, make sure to write an end case actually at the end of the case. So now that is done. Now save it. We'll check for any behavioral errors. Okay, now behavioral check is completed. We can proceed with proceed with RTL synthesis. Go to implementation, select the 7 segment display, and view RTL schematic for this. Okay, like you see, like the 7 segment display is completed now, and this itself is directly like simulated as 7 segment display, and you cannot like go deeper into this module because this is the fundamental module that is directly used. Okay, so this is how you design the 7 segment display. And when you're writing the test bench, it is easy to decode also. So for example, this test bench I have already created. Okay, declare input as reg, output as wire y. Okay, and just adjust the delay actually between input. I keep it 10 nanoseconds. Okay, done. Save this. After saving, like check for behavioral syntax if any errors are present. No errors are present. Go to simulations and simulate the behavioral model for test bench. Okay, now our model is completed. Okay, yeah. So you can see like the input data and how the 7 segment is changing. We can like drag this input data first. Yeah. So for 0040's output is this output. For 1 it is this output. you can also like expand this to see each bit. Similarly for 0010 output is this, and so on for other data. So data is completed successfully. So after like data becomes 9, okay, it goes to the, it stays this value actually, and it won't change after that. Okay, because we didn't provide any input after 9. This is why like since we didn't provide input after 9, the output is like remained same only, so it has not changed. Okay, so this is how we can like we have like developed a test bench. So for using the case statement using Verilog, and also we have shown how like the always statement can be used to design combinational logic also, and not limited to sequential logic. So yeah, this is it for the video, and let me know if you have any doubts in the comment section. Thank you.